In this video, we're going to be shifting gears a little bit. So we were talking about conic sections. Now we are talking about sequences and series. This is chapter 11. So I've already walked through this video, but my video got corrupted. So I already have the notes for it. So we're going to talk through some of these and hopefully make some sense. All right. So we start off with 11.1. 11.1 is on sequences and summation notation. And the general idea here is we need to kind of figure out what's the difference between a sequence and a series. Yeah, because we are talking about this chapter, which is sequences and series, so you should know the difference between the two. So what we see is with a sequence is just an ordered list of numbers. So that might be something like 1, 3, 5, 7, 9, 11, whatever. This list, right, comma separated, this list of numbers is going to be defined as a sequence, whereas a series is going to be the sum of these numbers or values, right? So that is 1 plus 3 plus 5 plus 7 plus blah, 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 yeah? So again, sequence is just the list. The series is the sum, the addition of the two, okay? Now, from here, we'll kind of talk about both, right? Sequence and series, but since we're in 11.1, we're going to start with sequences. And so with sequences, we can think of this almost like a function. Yeah. So we have like a formula essentially that we're going to have that we're going to plug into. But the caveat for a sequence is that the domain is the set of positive integers, right? So what that means is when we go term by term, you can't plug in something like 1.3 or 2.7. You have to plug in positive integers. So 1, 2, 3, 4, 5, and so on. So this is kind of a general way we write our sequence out. We'd have our first term A1, and then we have A2, A3, A4. So this is first term, second term, third term, fourth term, blah, 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 until we get to A sub n, which is our general or nth term, right? So this is kind of the formula part that we would have, right? A sub n has this general pattern to it, okay? So again, we have all these terms, yeah, that we're going to have in our list, and n corresponds to what number term we are at. And n has to be, of course, a positive integer, as we talked about. Okay. So as we go through this, yeah, we can kind of give an example. And let's say the nth term, the general term, is a sub n equals n over n plus 1. So this is the pattern that we will use to create any term that we want in our sequence. And the question asks us to find the first four terms, and then we want to find the 10th term. So we want to find A1, A2, A3, A4, and then we want to find A10. So what I've done is kind of did that down here, where I essentially plug in n is 1, n is 2, n is 3, n is 4, and n is 10 into my top formula. So for example, the first one, A1, yeah? A1, you will plug in to our formula, n being 1. So I plug in 1 over 1 plus 1. That gives me half. A1 is a half. And then my second term, A2, is where I plug in n to be 2. So 2 over 2 plus 1. So 2 over 3, and I repeat the process, 3 over 3 plus 1, 4 over 4 plus 1, 10 over 10 plus 1 for each of my n values, okay? So I'm just getting my general form, or my nth term here for the sequence, and then you're just plugging in numbers to find that term in the sequence, okay? Very straightforward. What we can also do is we can give you kind of the numbers from the sequence, and you have to create the general or nth term, right? You need to basically determine what the pattern is. So in these examples here, 2, 4, 6, 8, 10, 12, 14, blah, 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 blah. This is my first term, A1. 4 is my A2. What we notice is that the formula, assuming we start at obviously n equals 1, right? So we're assuming this first term is n1. Sometimes we can make that a different term, like a n0 or n2 or n5 or something. But to start, we start with, say, n is 1 as the first term. A sub n equals 2n would make sense here, right? So if n is 1, 2 times 1. If n is 2, 2 times 2, 2 times 3, 2 times 4, 2 times 5, 2. So this would be a pretty straightforward pattern because everything is just going to be increasing by 2, right? Another pattern we could see is 1, -4, 9, -16, and so on. Not only does our numbers increase here, we are getting this kind of alternating pattern, right? Negative, positive, negative, positive, negative, positive. So what we'll need to do is we'll definitely need to account for the change in sign, which will be this like alternating factor is what we call it, this -1 to some power. And then we'll also need to obviously account for the fact that we're going 1, 4, 9, 16, and so on, which will be taken care of over here. Okay, so what we'll notice is that if I need the first term positive and the second term negative, the third positive, fourth negative, every even is actually negative and every odd is positive, right? And 1 positive and 3 positive and 2 negative and 4 negative. So we want to basically do -1, but you don't want to do -1 at the end because remember, -1 at the end, when it's squared, it would be positive. When it's 4, it would be positive. When it's 6, it would be positive. I want to flip that, so I'm just going to add a +1. That way it shifts the sign to be all odds instead of all evens. Yeah. And then the pattern is 1, 4, 9, 16, 25, 36, and so on. So this is n squared, right? 1 squared, 2 squared, 3 squared, 4 squared, and so on. So you would need that n squared. So this would be the general term. Okay. Again, as you can see, there is a pattern recognition happening here, right? You need to basically be able to recognize what this is, and it's easier once you've done a couple and you've seen a couple, you kind of start to see the patterns. But a lot of it's like addition, subtraction. You're looking for multiplication, division. You're sometimes looking for like squared or cube things. Sometimes you're looking for, like we see the alternating pattern, you might have something like that, or we even might see some factorial stuff. So it's like 1 times 2 times 3 times 4. So you have this pattern where you are going to be multiplying by numbers leading up to that value. We'll take a look at those later on as well, but something to keep in mind, right? You're going to have to kind of find these patterns and start to be on the lookout for them. What we also see is we can have these recursively defined sequences. So what that means is recursion happens when things rely on things that have happened in the past, right? So in our example, this would be you give the first term, a1 is 3, and then every future term is dependent on the term before it, right? And this could be not just the first term right before it. So this is like a sub n and a sub n minus 1. So that's like the term right before. This could be n minus 2, n minus 4, whatever. So basically what we see is that if I wanted to get a sub 2, second term, I would have to do 2 times a sub 2 minus 1, a sub 1. So to get the second term, you need to know the first term. And then to get the third one, you would need to know the second one, and vice versa. Yeah. So what I did over here was I basically just found a couple. So first term 3 given, easy. The second term, like I just said, you would plug in n is 2, which means 2 minus 1 becomes 1. So you want the a sub 1, first term. Well, first term was 3. You plug that in, I got 7. And then to get third term, I need to plug in the 3 minus 1, 2. Second term was 7. So I plugged in 7, and I got 15. And then to get the fourth one, I plug in the third term, 15. And then to get the fifth one, I plug in the fourth one, 31, which is all dependent on the one before that, right? Back. So recursive sequences, right, recursively defined, is going to depend on previous terms. Okay. From here, we start to look at the series part. Remember, the series was the sum of those terms, whereas the sequence was just the list. We have something of importance here called the partial sum of a sequence, and this is just going to be the addition of a certain amount of terms, right? We can define what that is. Maybe it's s sub 5. That means we want to sum the first 5 terms, whatever. We're going to establish that number, right? Figure out what we need. So the general form of writing a partial sum, we use big S, sum, pretty straightforward. And then n subscript, that's going to be labeling the term we want, just like we were doing kind of with the sequence terms, right? We did like a sub n, you're going to do s sub n. And this is going to correspond to the sum of that many terms. So if you look at s sub 1 would be a1. But s sub 2 would be a1 plus a2 because it is the sum of the first 2 terms. And then s sub 3 would be a1 plus a2 plus a3. And the list would go on and on and on. You would continue to sum until you got s sub n, which would be the sum of the first n terms, right? So that is a partial sum because you are only adding part of the sequence, right? Like s sub 3, this would be part of the sequence, only the first 3 terms. We also have something called the infinite series, which is going to be what we could kind of define as s sub infinity. You can imagine that means infinitely many terms, and so your list goes on forever, right? You don't stop at a sub n here. You keep going plus forever. We're not going to talk about infinite series here in this class. This comes up a lot in Calc 2. So you will be doing a lot of infinite series in Calc 2. I just kind of wanted to introduce this and say, obviously, we could sum this forever, but the problem is we don't know how to sum infinite things, right? We know how to sum finite things. I know how to add a couple together. There's a lot of special nuances when you start going towards infinity, which we've not discussed here. Okay, but keep that in mind. We will come back to this eventually. So it's important to know how to work with these sequences and series. Now from here, we kind of shift to talk about sigma or summation notation. And this is essentially just a shorthand for us to be able to add things, right? To sum things. So we just talked about we're trying to do these partial sums, but what happens when you want to find the sum of the first 20 terms? I don't want to have to do this plus this plus this 20 times, right? You're not going to want to write all of those numbers out by hand. Instead, what we do is we create this kind of shorthand, which allows us to write this summation a little bit neater, right? So for example, if I have this over here, a1 plus a2 plus plus a, so this goes all the way to however many n terms we have. Instead of writing this entire list out like this would be equivalent to this left-hand side over here. So what we see is that we have this summation. So this symbol here is this Greek sigma. And this will say to sum or to add, right? So we have the sigma and the sum or add. We start with this value at the bottom and we go up to this value at the top. So here we're saying, hey, we're going to start at 1 and we're going to go up to n. That's why we have 1, 2, 3, 4, all the way up to n. So you have your starting index and your ending index, where you start and where you end. And I add all those up from that starting point to any point. We're using this a sub n as the formula. So this is the general term that we talked about. This is my formula. So this is what I'm plugging in. So when I is 1 here, I'm plugging in 1. When I is 2, I'm plugging in 2. Technically, this should read as a sub I. So if you're using the I as your index, so here we have this index of summation. This is the thing that you're going to be adding across, right? So I starts at 1 is what we're saying here. So I is starting at 1, and we're going to keep adding more and more and more all the way up till n. So I is 1, I is 2, I is 3, 4, 2, 2, all the way up to n. Yeah. So that's our index of summation. So we start here, add up here, and we plug into the general formula. You get this. A couple examples to try and make some sense of this is here we talk about the summation from k equals 1 to 5 of k squared. So that means I'm going to start when k is 1. I'm going to go k2, k3, k4, k5, up to 5. And I'm going to add all those together because the summation says add those things. And all of those numbers are going to be plugged into k squared. So this is k is 1, k is 2, k is 3, k is 4, k is 5. I add those up and I get a final value. I didn't add these up, but we could add them up and you get obviously your final answer. Fine, right? Maybe you do it by hand, maybe you do a calculator. We do get a final value. That's what our summation is going to be. Okay. Similarly, in another case, note here that we can change the index of summation. So it doesn't always have to be I or K. Generally, these are the two letters that we do use when we do summation, just because these are not ones that we frequently have in other equations, right? Like we don't use X or Y or whatever because we use X and Y a lot, but I and K are very common ones. Some J as well, M, N, L, P, like we don't use those letters usually. So those would be good ones to kind of work with. So in this one, we have summation I equals 0 to 4 of 1 over I plus 1. So that means, hey, I0 plug in, plus I1 plug in, plus I2 plug in, I3 plug in, I4 plug in, add them all up. This is I0, I1, I2, I3, I4. I plugged them all into the general term, nth term, and then I sum them all up, plus, 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 plus. Final answer, whatever that is, right? Again, these are fractions. Maybe you do this by hand, get a common denominator, or you just use your calculator. Whatever the answer is, you get a final answer. That is the summation. Okay. Hopefully this is pretty straightforward, right? We're just using kind of a more shorthand summation notation or sigma notation. We can also take some sum that's written out and obviously rewrite it as summation notation. So for example, 1 plus 4 plus 9 plus 16 plus 25. What I notice is that this is a similar pattern to what we talked about earlier, which is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And so that is n squared is my formula. And I have 5 terms, so I'm going to summation, right, sum 1 to 5. And it makes sense because this is 1 squared, 2 squared. We already talked about what the number should have been, so that would be n is 1 to 5 to make it work. Okay. If this kept going on forever, right, or infinite series, then you would just sum from 1 to infinity, right? Your starting point is 1, and then we just keep going on forever. So we would sum up to infinity. Again, we're not going to talk about infinite series in this class, but this will come back in Calc 2. So again, just something to think about using the same notation. There's nothing different. We're just adding infinitely many terms. Okay. Okay. So from here, right, we talked about generically these sequences, kind of what they mean, how to work with them, find some partial sums, things like that. Now we look at a particular type of sequence, an arithmetic sequence, right? So an arithmetic sequence, this is 11, 2. An arithmetic sequence is just a sequence whose term is going to differ from the previous term by the same fixed value, right? So the next term and the previous term, wherever you are, they're going to have this relationship from one another, and it's going to be the same difference every time. It's always going to be the same fixed amount every time. So what that means is in our form here, and this is our arithmetic sequence right now, the first term we call A. The next term will be the first term plus some what we call a common difference, a d value, which is the common difference, so plus some d value. And then the next term would be the same thing before it, a plus d, and you just add another difference, another common difference, d. So since you already had a d and you add another d, you get 2d, and then you get another one, 3d from the next term, and then 4d and 5d and so on. So every single term is just plus the common difference, plus the common difference, plus the common difference. So what that means is if you wanted to find the common difference, which usually we'll want to do, right? We'll want to find the common difference because this is important for the pattern of the sequence. You will just take your current term, whatever that is, right? A sub n or whatever you want to call it, and you'll subtract the previous term. So if this is A2, you subtract A1, right? You take the next term minus the previous term, you will get the difference between the two. So that will always work no matter what you choose. This minus this will always be D. This minus this will always be D. You obviously just have to do the ones next to each other. You can't jump this term to this term. That wouldn't make any sense because those are not the next and the previous, right? That's 2 away. So that would be one way we could find our difference. And what we also see is that if I want to determine the nth term, so I want to get like a general formula for my arithmetic sequence, we can actually use this formula here. So a sub n will actually be equal to a, first term, plus n minus 1 times d. So the n minus 1, let's think about this really quickly. Where is this kind of coming from, right? The n minus 1 is because if this is first term, we'll call n1, and then this is second term n2, and this is third term n3, let's say. Note how the number in front is 1 less, right? And this one doesn't even have a d, which makes sense. 1 less would be 0 d's, right? 0 common differences. So what we're noticing is that we need to shift back one because the first term needs to be accounted for, yeah? You want to make sure that you don't include any common difference for the first term because A1 would just be first term. You want D to be 0. You don't want to scale by any common difference, right? But then once you go n is 2, you'll want to add 1d, which means 2 minus 1, that would be 1d. If you want n is 3, you'll want to plug in 3. 3 minus 1 would be 2 of the d's, which is from the formula. So it makes sense that we would need to just slightly shift back by 1 to make sure that we don't include an extra term for no reason, right? We have to account for the first term not having any common difference. Okay, hopefully that is making some sense. So let's take a look at a couple practice problems here. Start us off with this example, 5, 8, 11, 14, and so on. The first question is going to say, hey, is this an arithmetic sequence, right? And the way we do that is we would look at the numbers and we would try and figure out, is there a common difference? And what we do is, we can take this term and subtract from this one. And we see that 14 minus 11 is 3. We can then do 11 and 8. We see that subtracted from 8 is 3. 8 minus 5 would be 3. 3, 3, 3, 3, 3. It's all 3's, right? And so the difference is 3. We go 3 every time to get to the next term. And so, yes, it is an arithmetic sequence, and the common difference is 3. Okay, so we're going to be looking for the pattern, and we're going to see if all the terms always have the same difference, then it would be an arithmetic. If this went 5, 8, 11, and then this jumped to 15, I would see that we had a pattern of 3 early on, but then somehow we kind of jumped and had a pattern of 4. That wouldn't work, right? That means it's not arithmetic. It has to be the same difference throughout the entire thing, right? It has to be the same difference throughout the entire sequence you have, entire list. Another one, 3, 7, 11, 15, and so on. What we notice is that it is arithmetic and the difference is 4, right? Common difference is 4. We should kind of recognize that right away. 15 minus 11, 4. 11 minus 7, 4. 7 minus 3, 4. Easy. Now with this, right, we're probably not just asked what's the common difference. We want to know what is maybe the formula for the general term, or we want to know what is the 20th term, right? So you would need to be able to use that formula we talked about. So plug into, for example, a sub n. First term we established was 3. N is just n. We don't know what we're plugging in yet, right? We're not here yet. We're just plugging in some arbitrary n, and then the difference is 4. So this would be a totally acceptable answer for us. We just plug in our values, we get this. If you want, you could kind of expand this out, simplify a little bit more. You get 4 and minus 1. It also works, right? So these are equivalent. So either would be fine. And then we would use this to find the 20th term. So either here I plug in 20 for n, or here I plug in 20 for n. Nonetheless, we get an answer of 79, right? So the 20th term would equal 79 in this sequence here. Okay. Hopefully this is making sense, right? So common difference, we add these things for an arithmetic sequence, and we can use that knowledge of the addition and how many we need to find other terms, right? Given one term, you can find the other ones because we know what the difference between them should be, right? It's some number times the common difference. Now back to this partial sum, right? Again, we do need to eventually get to series, yeah? So we're talking about these partial sums. And for an arithmetic, we want to find the formula, right? Some generic formula we can use to find the partial sums. We don't want to have to solve these obviously by hand. And so to derive this, perhaps a little bit counterintuitive process, but I'm going to work through it here. You won't need to know, obviously, to do the full derivation, but we need to know the final answer, right? The formulas. So as we work through this, let me start by just creating a generic equation for the sum of some n terms, right? The sum of the n terms of a arithmetic would be first term plus second term plus third term and so on, all the way up to the nth term. And then what I'm going to do is I'm going to actually add the same formula again. I'm going to add the formula to itself. But what I did was I kind of flipped the order of the values. So instead of going from first term to nth term, I go nth term down to first term. And what I notice is that if this is the nth term, then the term right after it, right, which is the n minus 1 term, this would just be the nth term minus the difference. Just like if I'm going up, I'm adding the difference, I can subtract the difference and go backwards. It makes perfect sense, right? Either I'm adding 2 to go forward or I'm subtracting 2 to go backwards, right? So I do this because when I add every column now, so I'm going to add these two together, I look at each one, and so this column here becomes 2 s of n, makes sense. This becomes a plus a sub n. This becomes a plus a sub n. The d and the minus d, those go away. The common difference cancel, so you get a plus a sub n. That's another a plus a sub n. Same thing here, these go away, you get a plus a sub n. So I'm actually seeing a pattern where every single column gives me a plus a sub n. And if you have n of those things, because you're going first term, second term, third, all the way to n, so there is n columns, right? 1, 2, 3, 4, 5, 7, all the way to n. You have n a plus a sub n's. And so your formula is just divide this 2 over here to get s sub n by itself. You get n over 2 times a plus a sub n. Cool. I have this formula for my partial sum. Now, looking at this formula is dependent on if you know what the first term is, what you know the nth term is, right? And obviously, once you know you're looking for some 20th term or whatever, you know n, but these kind of go hand in hand. You need to know this first term and then some other term. You need to know 2 terms basically. What happens when you don't have two terms, right? What happens when you only have the first term, or maybe you only have the 20th term, you don't know the first term? You need another way to find this given different information, yeah? So given different pieces, you might need to use a slightly different formula, and that formula would be where I just replace a sub n with the formula we talked about, which is a plus n minus 1d, the formula to find the nth term, right? So the benefit of doing this, if I plug that in, I actually get a formula here, which is only dependent on the first term and the common difference. Obviously n as well, but like that's to know, like if I want the sum of the first 20 terms, n is given to you, right? It's assumed that you're already given kind of n. So you only have two really unknowns, the first term and the difference, which is actually usually given, right? If you have a sequence of terms written out, your list, you could see the first term visually and you could find the difference visually. You just look at the next term, subtract the previous one, you can find it. So this could be a more common formula you use just because of the fact that it has less limited requirements, right? You have this information usually always, whereas here you're not always given the nth term's value. Okay. So with this being said, right, these two formulas, let's go ahead and try a practice problem. I'll keep these up in view so we can work on this. So let's say we want to find the sum of the first 40 terms of an arithmetic sequence that's defined by 2, 5, 8, 11, and so on. Okay, so first 40 terms, we want to sum those. We know it's arithmetic, and we're given the pattern for it. Okay. So here it should be known that A is 2, first term 2. Yep. Common difference is 3. Yep. 3, 3, 3, so on. So plugging that in, right? You only know A, you only know D. Makes more sense to plug here in than it makes to plug in here, right? We don't know what the 40th term is. If I did know the 40th term, if I had that over here, that'd be awesome, but I don't. So we plug into the second form, and we get S sub 40 equals 40 over 2, 40 over 2, 2 times 2 plus 40 minus 1 times 3. Okay, 40 over 2 is 20, 2 and 2, 4, 40 minus 1 is 39, 39 times 3 would be 117, 4 would be 121, times 20, 2 times 121 is 242, add an extra 0, my final answer becomes 2,420. Right, so again, just kind of plug it in the formula, we find that the sum of the first 40 terms is 2,420. Okay. Awesome. Again, we will need to know these formulas, right? So add these to the list of things that you will need to make sure you have down. All right. Now, from here, we can also talk about our geometric sequences. I didn't go too much into this yet, but let's go ahead and take a look at our geometric sequences. So with geometric sequences, I want us to think back to what we saw with the arithmetic, right? Arithmetic was we added the same term over and over and over again, right? It was every difference was the same. Every single time, difference, same. With a geometric, we are also going to have the same value, but it's not going to be added. It's actually going to be multiplied. So a geometric sequence is going to be a sequence in which each term is found by multiplying. So by multiplying the previous term by the same fixed amount. Okay, so very similar to the arithmetic, except we're not adding, we are multiplying. Okay, so we are multiplying the same fixed value, we're not adding it. What does that look like in terms of our pattern? Well, this would look something like A times R, A times R squared, A times R cubed, and so on. So every next term you multiply by R, which is going to be our common ratio, and then you do it again times R, then do it again times R. So every term is just going to be times R times R times R. Okay, remember R, common ratio. A is still our first term. We have the same type of info we had last time, right? All right, so let's think about this then. To get the common ratio, you could take the next term and divide it by the previous, right? So you could take a sub n plus 1 divided by a to the n, which is the same thing as taking a to the n over a to the n minus 1, right? So call this n minus 1, call this n plus 1. Whatever you want to do, right? As long as you take the next term divided by the previous term, you will find the common ratio. Okay? Now, to get the general term, a sub n, think about this. If I want the n is 1, n is 2, n is 3, n is 4, and so on. If I wanted the fourth term, the pattern would be a times r to the n minus 1. I take one less than the term I'm trying to find, right? If I'm trying to find the fourth term, I'll take 4 minus 1, I'll get r cubed. If I want to find the third term, I'll take 3 minus 1 to get 2, and the process will repeat, yeah? So this is going to be our general term for a geometric sequence, right? Now, we're going to work the same way we did with our arithmetic. We're going to find all the same pieces. We're going to do the same deal with our partial sums. Not much is going to be different. It's just a different ratio now, right? We're multiplying instead of adding. So let's pop a couple examples on here to try and make some sense of this as well. Let's say I've got, I don't know, 3, 6, 12, 24, and so on. First, I'd identify that this is geometric and not arithmetic, right? It's geometric because times 2, times 2, times 2. You can't add the same number every time, right? This one was plus 3, but then this is plus 6, this is plus 12. You're not adding the same fixed amount. So there's not an addition, it's a multiplication, right? Times 2, times 2, times 2. 2 times 2. So what do we see? Well, we see it's geometric. So geometric sequence with our R value of 2, right? You can find that by doing 12 divided by 6, 24 divided by 12, 6 divided by 3, whatever it is, yeah? So geometric sequence with R equals 2. Okay? Do another example. Let's say I have the sequence 5, 10, 20, 40, dot, 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 and I want to find the nth term and the 7th term. Okay. Again, is this geometric? Yes. Yes, it is. Yeah. So times 2, times 2, times 2. Again, I did 2 here. It doesn't have to be 2, right? Yeah. It could be mu multiplied by half. It could be mu multiplied by 5/3. It could be whatever. So we're multiplying by 2, right? Times 2, times 2, times 2. So my R is 2. Therefore, my general term, my nth term, remember a sub n, go slightly bit up here. A sub n was a times r to the n minus 1. So this would be a times r to the n minus 1, which is a r n minus 1. So it's 5 times 2 to the power of n minus 1. If I want to find the 7th term, you would do 5 times 2 to the 7 minus 1 to the 6. 5 times 2 to the 6. 2 to the 6 is 2, 4, 8, 16, 32, 64. Right? 2, 4, 8, 16, 32, 64. So 2 to the 6 is 64. And then we take 64. We are going to then multiply that by 5, and we will get 320. So the 7th term for this geometric sequence would be 320. Okay. Again, hopefully this is making some sense. We could also use the formula to find other things, right? So they could ask us here, okay, what's the 7th term? What's the nth term? They could say, what's the first term? What's the common ratio? We can ask any of the pieces that could be unknowns. So you'd have to think about your formula. What do you plug in? What are you finding? And just rearrange everything. I'm not going to do an infinite number of examples on all of those. I think, once we have the formula down, we can definitely figure that out, very similar to how we did with the arithmetic. All right. Now, the only thing that I would want to take a quick peek at before we kind of shift gears from our sequences, we want to talk about the partial sum of a geometric sequence. Okay, so partial sum of a geometric sequence. With our partial sums, we're going to do a very similar process to what we did with the arithmetic to derive it. Again, not the most intuitive to begin with, but once you see it, it actually makes a lot of sense. So what I'm going to do is I'm going to create the nth partial sum for my geometric sequence. So I will go a plus a sub r, a square, ar squared, right, plus dot dot dot, plus a r n minus 1. So this is the first term, second term, third term, all the way up to the nth term, right? Because remember, the nth term is r to the n minus 1. And then I'm going to do the same thing where I'm going to go ahead and try and create another line. But in this case, instead of going backwards, I'm actually going to go and multiply my equation by r. So everything gets scaled by r. So this would be first term, a times r. Well, I'm going to write it over here, a times r. So that's the first term, right? I just took this multiplied by r, you get this. And then the next one would be a times r times r, ar squared. So I'm just kind of aligning these so they always fit, a r n minus 1. And then I have an a r to the n, because if you take this one multiplied by r, you produce this term, right? So I just shifted everything slightly to the right one, so I didn't have this single term here, because I want to align these, right? The goal is I want to kind of look at these columns, okay? Okay, so here, now that I have this and I have this, what I'm going to do, instead of adding, I'm going to subtract. So I'm going to subtract this entire row. So what that means is if I subtract this, I get s minus r s of n. A, right? Subtracting nothing, so it's just a. A sub a times r times a times r minus a times r, gone. Ar squared minus ar squared, gone. Gone, 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 gone. Nothing. Minus this is minus a r to the n. Okay, this should be s of n. Pulling out an s of n, you get 1 minus r, right? I'm going to factor s of n out. I get this. Here I'm going to pull out an a as well. So factor out an s of n from these two terms, factor out an a from these two terms. I therefore find the sum, s of n, is a times 1 minus r to the n over 1 minus r. So note that this is like its own whole thing. I'm just going to multiply it outside. Okay. So this is my equation for the partial sum of a geometric sequence, right? A little bit more sophisticated of a formula, right? I should also note, of course, this only works for finite number of terms. So it's not going to be a formula that works for the infinite number. Same as with all these, right? All these formulas, we're using this for the finite number, right? So the sequences are all finite. We're not doing any infinite yet. That's saved for Calc 2. So we would just want to plug into this formula if we needed to find the partial sum of some n terms. Yes? I'll go ahead and write something out here for us so we can see this in action. Let's say I want to find the sum of the first 8 terms of the geometric sequence. So here you're told it, but we probably could have figured it out. 1, 3, 9, 27, dot, dot. So you want to find the sum of the first 8 terms of this geometric sequence. How are we going to do this? Well, according to this, all you need to know is the first term and the ratio, common ratio. Well, I know that the first term is 1. I know that the ratio, as you can hopefully see, is 3, right? So 3 divided by 1 is 3, 9 divided by 3 is 3, 27 divided by 9 is 3. It takes 3 to multiply every time to get to the next term. So therefore, the sum of the first 8 terms is the first term, which is not 3, right? It's 1, times 1 minus 3 to the n, 8, over 1 minus r, which is 3. So here, you got to figure this out. I don't know what 3 to the 8 is. I could plug it in, right? But whatever this is as my final number, right? We plug that in, calculator probably, and simplify that. That would be the sum of those terms. Okay. So hopefully that's making sense, right? We would get this value. Note that this will become obviously a positive. So you're adding these numbers, it'll be positive. The top just becomes a negative because we're doing 1 minus something really big, and the bottom is -2. So the negatives will go away. You'll get a positive. It'll work out. You just have to compute that number. All right. So this is our portion on sequences, and we didn't really do a lot of series. We did the partial sums, which is kind of, it is a series. It's an addition, right? So we talked about these sequences in series. Hopefully these are making sense. We're focusing on arithmetic and geometric. We have 2 more sections to go, 11.5 and 11.6, which will happen in a separate video. Okay. All right. See everyone then.